There are different category of forces here in classical mechanics course, or maybe in electricity and magnetism course. In addition to that, in an atomic physics or nuclear physics courses, we're going to refer here some types of these forces. The first type of these forces, that of the contact forces. Well, actually, a contact force comes up due to interaction between the atoms of in the surfaces of the two bodies in contact. For example, if you want to pull or push an object, there is a contact between your hand and the object, and there's kind of interaction between the two. So this is an example for a contact between the two bodies. Also, the normal force acting on an object is considered as a contact force, in addition to that of the friction force. The tension in the rope is an example of a contact force, as long as the rope is attached to the mass. So this is considered as a contact force. But it is important to mention here that if a person holds the other end of the rope and trying to put a force on the rope, that force is going to transmit it all over the rope up until it reaches the object. But the actual force that acts on the object in the mass, attached to the rope, is the rope. An ideal rope may be that rope which doesn't stretch with the zero mass. There are other forces that act at a distance, like the gravitational force, for example. And as I mentioned before a while, there are other forces in electricity and magnetism, like the electric force, which act at a distance as well between any two charges, or also the magnetic force that between for example, two electric dipoles, if you like, magnetic dipoles. And the gravitational force will be demonstrated later on. These three diagrams show a normal force in different situations. The first diagram to the left shows a normal force acting from the black surface on the object of 2 kg upward. That is normal to the surface. However, the force of gravity is, as you can see, is always downward, and it is nothing more than the product of the mass of the object and the acceleration due to gravity. The second diagram shows the normal force perpendicular to the incline, because the inclined surface is pushing this red object in a way perpendicular to its surface, as shown in the figure. However, the force of gravity is still acting downward, as you know. Now, the third example, the blackboard is set in this way, where the object is is trying to be pushed by a force in this direction against the blackboard or the black object where the force of gravity is downward. Let's see where is the normal force. Well, the normal force, as we said, is the force acted by the black board or the black object on the object in this direction to the left, as seen in the figure to the left. So we should here mention again that the normal force is always directed perpendicular to the contact surface. Well, the question might ask, what about if the object is put in a curved path or curved surface? How can we decide the normal force? Simply, at the contact of the object with the curved surface, you take a tangent, and perpendicular to that tangent is going to be the normal force if the curve is up or down. So that means the force will be either towards the center of this curvature or outward. It depends how did you place the object. Is it on the inside of the curved path or outside it? The tension as an example for a contact force can be seen in these two diagrams. The diagram to the right is a rope holding the object stationary against the force of gravity, and the tension in the rope is upward. While the one to the left, the rope is attached also to the mass, but it's gone through a pulley and then to the left, and it's fixed on the surfaces here. So the tension in the rope is not straight up like here, it's bended as shown in the figure. But still, this mass is in equilibrium under the action of the contact force tension, and also that is equivalent to the force of gravity, which is pulling down. And in these two cases, the object is stationary in equilibrium, in static equilibrium.
When a piece of clothing is hung on a clothesline, the clothesline always droops. This mass has a weight of about 5 newtons, as shown by this spring scale. If we attach the spring scale to one end of the line and then hang the mass in the center, how much force will have to be applied to completely straighten the line? 5 newtons, 10 newtons, or more? Even 50 newtons will not completely straighten the line. The force required to get the line perfectly straight is infinitely large. This animation shows the gravitational force pulling down on the hanging mass and the tension forces in the rope as the tension is increased. For the system to be in equilibrium, the sum of the two tension forces must be equal but opposite to the gravitational force on the hanging mass. This cart on an incline is acted on by 3 forces: a downward gravitational force, a force along the direction of the incline supplied by this weight and string, and a force perpendicular to the incline provided by the incline itself. A mass hanging over this pulley will provide a force equal to the force from the incline. At this point, do we need the incline? The incline is no longer needed. It can be removed and the cart will stay in place.
Pulleys have two main purposes: changing the direction of a force and reducing the force needed to lift an object through mechanical advantage. This metal cylinder has a weight of about 10 newtons. If we hang the weight on a string passing over this pulley, it still requires 10 newtons to lift the weight. The direction of the force is changed, but its magnitude remains the same. If we hook the end of the string to a fixed point and hang the weight from this free-running pulley, only 5 newtons are required to lift the weight, but the weight being lifted only travels half as far as the scale doing the lifting. We use this system of spring scales to illustrate one aspect of how a pulley works. The lower spring scale hangs from the top of this frame, with a pulley hanging from the bottom of the scale. A rope attached to the bottom of the frame passes over the pulley and hangs freely. If the free end is gently pulled, a force is exerted on the spring scale. The frame is then suspended from the upper spring scale. The weight of the frame system is about 5 newtons. If the free end of the rope passing over the pulley is gently pulled until the lower scale reads 10 newtons, what will the upper scale read? 5, 10, or 15 newtons? Why do we get this surprising result? Because the pulley is attached directly to the lower scale, it doubles the force in that scale, but has no effect on the upper scale to which it is not attached.
As we said before, gravitational force is a kind of force that acts at a distance, and the force between two masses which are not in contact with each other is inversely proportional to the distance between the two masses and directly proportional to the product of the masses. In this relation, the force F has a constant of relation called G, which is the universal constant of gravity. G as a value is 6.67 times 10 to the minus 11 Newton meter square per kilogram square in the System International. As we said before, that the force, gravitational force, is equal to G times the product of the masses, of the interacting masses, divided by the distance between them. The question you might ask, how did we get the force due to gravity of mass times the acceleration due to gravity small g? Well, to see that, let's demonstrate the following. If we consider m1 as the mass of the Earth, and then we insert that into the relation, we're going to get force equal G times mass of the Earth by the mass of the object divided by r square. Now, here in this situation, the force will be exerted by the Earth on the mass, and this force will be called as weight. If you are near the surface of the Earth, you're going to substitute instead of r the radius of the Earth, if the object is on the surface of the Earth, obviously. Then you have G, big G, m sub e, the mass of the Earth, divided by the radius of the Earth. And then these three, G and m sub e and r sub e, are given as constants, which is reduced to the value of G acceleration due to gravity on the surface of the Earth. and then you get the weight is a product of m2 times g, where the mass of the Earth is 5.98 times 10 to the power 24 kilogram, and the radius, its radius is 6,400 kilometers. If you put all these values into the relation together with g, you're going to get an answer of 9.8 meter per second square. That is the acceleration due to gravity near the surface of the Earth, and we usually use it in our problem. Now, the acceleration due to gravity can be obtained as the force of a gravity divided by the object m, and obviously this g is usually called acceleration due to gravity, which has a value, as we said before, of 9.8 meter per second square, and it's directed downward, as you know, the same as the direction of the weight, as you know.